Significant figures. So to do math a lot of times in chemistry, you have to understand the significant figures in the problem. Significant figures are telling us, they're explaining to us, okay, the accuracy or the precision within a measurement of data. So we're given data, and we have to use that data to calculate something, some sort of math equation, and we have to know on our from our calculator how many numbers from my calculator do I keep. Do I just take the whole list, which is like 20 numbers, or do I just take 4 or 5 of them? Well, the significant digits are going to tell us. They will tell us how many numbers we use in the answer. Okay. So let's look at how you obtain a significant digit. So here is a ruler. Look at the top one. When I measure that line with that ruler, I have a certainty that that line goes after 5, right? There's no question about that. It passes 5. But the uncertainty is how far after 5 does it pass? So in this case, they chose to say it goes 0.4 after 5. They could have said 0.3, or they could have said 0.5, right? So it could have been 5.3, 5.4, or 5.5. It is a guess. That is the guess. That's the uncertainty in the number. And that tells us the last significant digit. The last significant digit in a measurement is the guess digit, the one that I have to guess. So a lot of times when people are weighing stuff on the scale in the lab, on the balance, they will see there's a whole bunch of numbers on there, and they write them all down, and then the last number they're like, I have no idea what to write because it just goes up and down, up and down, up and down. That's because the scale is guessing that last digit. That is the last significant digit. And therefore you have to guess what it is. It's going from 3 to 5 to 4 to 2, okay, and you have to just take one of those numbers. It's a guess. That's all it is, and that's the last significant digit. So let's see how my significant digits change when I add precision to my ruler here. Okay. Now I know for certain it goes past 5, right? And I know for certain that it goes past 0.3, and it lies somewhere between 0.3 and 0.4. So now I have to add another significant digit. I have to guess where between 0.3 and 0.4 it lies. It lies at 5.36. I could have said 5.35 or 5.34 or 5.37. It's a guess. Okay? I don't know for certain where it is. I just know I have to guess that it's between those two numbers. Okay? And that's my last significant digit. So significant figures are all the digits in a number representing data, okay, or the results that are known with certainty, plus one uncertain digit. I have to guess it. Okay. So when I am given data or numbers and I want to identify the number of significant digits in that data, okay, these are the rules. All non-zero digits are significant. 7.314, everything there is significant. So really, you don't have to try to determine the number of significant digits unless there is a 0. The 0 is where you have to determine whether it is significant or not, because all other numbers are. It's independent of the decimal place, okay? As long as it's all numbers, non-zero digits, then they're significant. Now look at this number, 60.052. I have zeros. I have zeros here, and I have zeros here. I have to determine whether those zeros are significant. This rule is telling me how to do that. Zeros located between non-zero digits must be significant. So they are. So I would count here and I'd say there are 1, 2, 3, 4, 5 significant digits. 5 significant digits. Now, it's the zeros at the beginning and the end that trick us. Okay? Zeros at the end of a number are significant if the number contains a decimal point. So 4.70 has 3 significant digits because that 0 is significant. It's after the decimal, after a number, so it's significant. Trailing zeros are insignificant if the number does not contain a decimal point. Look at the number 100. It has 2 trailing zeros. They are insignificant. There's no decimal. They are insignificant. They are simply placeholders. They are simply maintaining the value of the number. So if I say it's insignificant, does that mean they're not important? No. They are very important. In fact, they're probably more important than whether they were significant, because it maintains the value. If I deposit $100 into my bank and they credit me $1 because it's just one significant digit, right? I'm not going to be very happy about that. These have value to them, but they are not significant digits. Okay? And so a lot of times people think significant means that they're very valuable zeros. No. If it's a significant zero, it's actually pretty unvaluable. It's an unvaluable number. But insignificant zeros are very valuable. They are very valuable. Okay? You got to start thinking backwards again. Okay? Chemistry is about being dyslexic. Okay? So you got to think backwards. If it is an important zero, then it's insignificant. If it's an unimportant zero, it's significant. Okay? Zeros to the left of the first non-zero integer are not significant. Look at these zeros. Are those important? Yeah, if I took them away, would that change the value of the number? They have value. They are important. So are they significant? No. If they are valuable, they're not significant. If they're valuable numbers, they're not significant. These are not significant. Exactly. Okay. These are not significant zeros. Why did I put them there? They're placeholders. They maintain the value of the number. They maintain the value of the number. Why did I put these zeros here? Because they maintain the value of the number. If I take them away, they change the number, right? So they are valuable. I have to have them. If I have a zero and I don't need it, that means it's significant. If I have a zero and I need it, that means it's insignificant. Okay?
Wait. Repeat that last part.
Okay. Let's look at this.
Okay.
Hopefully it's not. All right. See these 2 zeros right here? I have to determine whether they are significant or not. So I have to ask myself, if I take away those zeros, does it change the number, the value of the number?
No.
The value, yes, there you go. The value does not change if I remove them, right? It's 3.4 either way. So why the heck did I write them? Because they're significant. They're significant to the measuring device that I use. This is telling me my measuring device measures all the way to here, and I guessed the last number. That's the only reason I wrote those zeros. Because they don't change the value of the number. So how many significant digits are in this number? 4. Do I have to have these zeros to maintain the value of this number? So are they significant? Okay, well that's kind of tricky. Okay, if they're between numbers, let me go back to that. They have to be significant. So how many numbers? 4. Okay. Decimal place, that makes these significant. Okay, back to these ones. Do I have to put those? So are they significant? If I remove those, it changes the value of it, but what does that mean about these zeros? They're placeholders. So they're insignificant zeros. What about this zero? Significant. What about this one? This one on the end. Why did I write it? Yeah. Did I have to write it to maintain the value of the number? No. So why did I do it? Because I have to guess that last digit. That means that it's a significant digit. I'm sorry? Right here? Oh, this one. It doesn't really count for him. It's insignificant. It doesn't count. It's just a placeholder as well. Nope. 1, 2. I don't count these. 1, 2, 3, 4. 4 significant digits. I see every question.
I thought those numbers, like those 2 zeros, like after decimal point, I thought those like those don't change the numbers, right?
So they're insignificant digits. If I take them away, the number has changed, right?
Yeah.
So I have put them there as placeholders.
Oh, okay.
They're placeholders to maintain the value of them. They're valuable. This zero is not valuable. Okay? So it's significant because it doesn't add any value to the number. So I wrote it because I am trying to show the precision in my measuring device. My measuring device measures all the way to here, and I guess that number. All right? Don't worry, we'll do a few more. Get your brains working on this, okay? New concept. Okay, what do you think here? Is that number 3 significant? Are the zeros after it significant? Is the last zero significant? I don't need that zero, right? It's telling me that my measuring device goes all the way to 0.0. Or to the...
But it would still count as a significant because you put it there. Right?
So I have 1, 2, 3, 4. So there are 4 significant. Yeah, that's the uncertain digit. That's the guess number. That's right. Okay. Yes. Oh, not negative. Equals. Okay, equals 4. Right? So 4 significant digits in that number. It is significant. That's why I wrote it. Okay, if I take it off, what's the number? 300. So what is it right now? What number is this? Exactly. So why did I write that last 0? Because it's a significant digit. That is the only reason I wrote it. It doesn't change the value of the number, right? It's not changing it. So I wrote it because it's a significant digit. That's right. Yeah. Okay, you're just going to have to remember that if there's a decimal, that means that those are all significant. Everything that comes before it. That's exactly what that decimal is saying. This is the guess 0. That's why if they left off that decimal, you would assume that that's not a guess 0, right? But by putting it, they're saying this is your last guess number. And so that's why they put it there. Okay. You're not going to see that situation a lot, but that's why. Yes? If you put what in the calculator? Yes. Okay. If you were going to put it in your calculator in scientific notation, you'd have to put 300 points. You'd have to put 3.000 times 10 to the second for it to be accurate. Okay? Yeah. But it is 4 because this has how many significant digits? 1. This has 4 because I added a 0 that I didn't need there. It doesn't change the value, right? These are exactly the same number, correct? They're not going to change any multiplication, whether I put this or this in my calculator, right? But this is 4 significant digits because I wrote that 0 because it's telling me my measuring device has that much precision. Okay? So there are 1, 2, 3, 4. So when I record my answer from my calculator, I have to consider that. I have to consider this precision. So when I record my answer, I'm going to want to record 4 digits, because to maintain that accuracy in my calculation. Okay? All right, let's look at some more examples. How many significant digits are in the first number? 3. How many in the second number? 1. How many in this number? 6. Okay, I'm going to cross off all the significant digits. Come on. Okay, these are not significant because they're just placeholders. They're placeholders that maintain the value. They're very valuable. Okay? Significant digits are not valuable. They're only there because they are telling me about the precision of my measuring device. Okay? That's what they're doing. Good. How many in this top one? Good. 1, 2, 3, 4. Those last zeros are not significant. Okay? They're not significant. Good. You guys are getting better. All right? Okay? So that's how we're going to try to understand the significant digits in the data that we receive. So when we do our calculations, we will use the correct number of significant digits. All right, guys. These zeros, they don't have any value, so they are significant. So you ask yourself, if we're only asking about zeros at the beginning or the end of a number. We don't care about zeros that are sandwiched in the number because those are always significant. Okay? So we just care about zeros at the beginning and the end. That's what we want to know, whether they are significant or not. So these zeros are significant, so how many significant figures do I have in that number? 6. I'm sorry. Haven't got there yet. Okay. Are these zeros significant? Why not? They have value. If I remove them, does that change the value of the number? So they are valuable. So because they are valuable, they are not significant. Okay? All right. So how about these zeros? Yes. They're sandwiched, right? So they're definitely significant. So how many significant figures do I have in this number? 5. Okay, good. So we already know, just like above, are those zeros significant? No, because they are valuable. So they are not significant. Are these zeros significant? Okay, why? Exactly. They have no value. The number is exactly the same with or without those zeros. So why did I write them? Why did I take my precious time to write 2 zeros at the end of this number if it doesn't matter? Because they're significant figures. They are telling me that the measuring device that I use can measure all the way to here. That's the precision in the device. That's what it's telling me. Okay? But they have no other reason for being there. Okay? So how many significant figures are in this number? 5 also. How many significant figures are in this number? 3. Good. You guys are getting good at this. Okay? Barely? Barely is okay. Barely is alright. Barely means that you can do it. Okay? So, that's what I have to ask myself when I am trying to understand whether a number is significant or not. Okay? I need to know, does the 0 have value? If the answer is yes, then it is not significant. If the answer is no, then it is significant.
Good question.
Yes.
So the last number here, so it was 2.0005. Those 2 zeros.
This number?
Yeah.
So,
Yeah.
if I had numbers out here in the front?
Because that 0 was 2.
Yes. If it was 2.00375, then this would be 1, 2, 3, 4, 5, 6 significant figures. Because yes, those zeros would be sandwiched between significant digits. Okay, any other questions? before we move on from this? Yeah.
That the two-thirds and it was taken away, given the value, so you do have value.
These zeros right here, if I take those away, you're saying it changes the value? Okay, so if I enter into my calculator, let me rewrite it, 0.0036750 or 0.00375. If I enter that top number or this bottom number into my calculator, will my result in my calculator be different? Oh, okay. You were missing the decimal. Okay. All right. That's all it was then. So you can see now that those are not valuable zeros. Okay. So then this would just have, those zeros would be significant then. So it would be 3, 4, 5 significant digits. This has 5. This has 3. Okay. All right. So any other questions on significant figures? We're going to move on to scientific notation if you don't have any more questions. So scientific notation. Writing scientific notation. When I write scientific notation, this is what I do. I start with a number, and I want to simplify it because it's a big number, so I want to make it more simple to use or to work with. So what I do is I put my a decimal right after the first digit in the number. So in this case, that's 4. So I'm going to put a decimal right after 4. 4 point. Now, the numbers that I put after the decimal are all the significant digits. Are these zeros right here significant? No. Why? Because they're valuable. They have value to them. If I take it off, it changes the number. So they are not significant. I had to write them. So I put them there because I had to, not because I was just trying to identify the precision in my instrument. Okay? So those zeros don't have significance, so I leave them off. And I just write 4.3 times 10, and I move the decimal place from where it was to the new place. How many times did I move it? 1, 2, 3 times. Okay, it went 1, 2, 3. It moved 3 times. So I say 4.3 times 10 to the third. 10 to the third is 1,000. Okay, so 4.3 times 1,000, and I get 4,300. So this is how I write scientific notation. It's a way of simplifying a number that's really big so that we don't have to enter that really big number into our calculator. We can just enter a really small number into our calculator. Okay? And that makes it easier to work with. All right? Okay. All right. Cool. Thanks. All right. Now, I have to, like I said, I have to represent all the significant digits. So how many significant digits are in this number? 3. 1, 2, 3. This 0 is not significant because it is a valuable number. It has value to it. So if I remove it, it changes the number. So I have to write it. But it's not a significant digit. 1, 2, 3. So when I write this number, which they wrote incorrectly, by the way, okay, what should it be? To the third, right? 1, 2, 3. I have a hard time counting. All right. So it should be 5.34 times 10 to the third. So 5.34 times 1,000, in other words. If it was 10 to the fourth, that would be 5.34 times 10 to the, or 5.34 times 10,000. 10 to the 5th, 100,000. Okay? All right. So, now, what if this number was written differently? What if it was written as this? How many significant figures are in the number now? 4. So when I write the scientific notation, I have to include all of the significant digits. So instead of writing 5.34, I need to write 5.340. I have to include that 0 because it is now significant. Okay? But it's still 10 to the 3rd, not the 4th. Okay.
So the difference is the period?
The period. This forces that 0 to become significant. Okay, so this is one of those times when you just need to remember a period forces them to become significant. And you can't use the whole logic yeses, no, which isn't very logical, but okay? That period forces it to be. Same thing with sandwiching zeros. You just have to remember sandwich zeros are significant because you can't use the logic of yes or no on that. Okay? All right. Now, that's if I'm writing big numbers. What if I have a small number? How do I write that in scientific notation? Well, I do the same thing. I go to the very first digit, which is 5. I put a decimal there, right? I say 5.34, 5.34. And then I say times 10 to the, so 5.34 times 10. How many times did I move the decimal?
2.
1, 2. I moved it 2 times. But now I move it in the opposite direction. Okay? So I say to the negative 2. It's in the opposite direction. Instead of being in the forward direction, it's in the backwards direction, so I say negative. So 5.34 times 10 to the negative 2 means I moved it backwards 1, 2 places. Yes. 1, 2. Okay? It's negative 2. All right.
4.001 with a 0 is significant. Is there in the middle?
4.001. They are significant zeros. Okay. So let's practice a few numbers here. Okay, I want to write these in scientific notation. Let's start with the bottom one, this one. How am I going to write that in scientific notation? What am I going to write first? Okay, I'm going to say 2 point what? What did we say? If I'm going to write the scientific notation, I have to represent what? All the significant figures. Good job. Okay? I don't round. That's a very common mistake, and on the quiz you're going to have a number like this, something like that, and one of your choices is going to be like 2.6 times 10 to the, and how are you going to choose that? That's wrong. What is the correct way to write this number in scientific notation? 2.600511322006335. That's where I stop. Times 10 to the 3, 6, 9, 12, 15, 18. Okay? So, 2.600051132200635 times 10 to the 18. If I have significant digits, I have to represent them. They have to be represented. Would it be what? Okay, so in this case, good point. Okay, in this case, it's not really that big of a deal to write the scientific notation, right? It's not going to help you a lot. The point that I'm trying to help you understand, though, is you have to write all the significant figures. Okay, you can't round.
Using numbers after last time, like zeros, because of the 5, does that make those zeros significant?
These ones?
No, the ones in the front. Right after the 6.
These ones?
Because of that 5,
yes.
That makes it significant.
It's sandwiched between significant, so they're significant. You have to include them. Okay? The only zeros on this number that are not significant are these ones.
So if there was another digit behind those zeros, those would...
Then they would become significant, and you'd end up writing the whole number anyway.
So there'd be no point in doing it.
I guess not. There really wouldn't, except it'd be more work to put times 10 to the in the calculator. Okay? All right, now let's look at the top number. So now you should be able to write this one without trouble. How do I write that one on top? Good. 10 to the 6. Okay? That's how I write it in scientific notation. Okay, now, scientific notation, you're not usually going to have numbers like that. Usually you'll have something more like this. What is that number? Not in scientific notation. Oh.
It looks like a caterpillar.
A caterpillar? A centipede, right? Okay. So, somebody asked, when are we ever going to use a number that big? Well, guess what? That exact number right there, you're going to use over and over and over again.
Why?
Because that number in chemistry has great significance. Avogadro's number. That is Avogadro's number. Okay? And it will be used again and again. Because guess what? See those numbers up here on our table? Nitrogen, 14 grams. The mass of nitrogen is 14.0067 grams. That means if I have 14.0067 grams of nitrogen weighed out on a scale, let's say, I would know exactly how many atoms of nitrogen I have. That's how many it would be. It'd be exactly that many atoms of nitrogen. So if I weigh copper, 63.546 grams of copper on a scale, guess how many atoms of copper I have? I have that many. That's a lot of atoms, right? That's how many atoms I need to make that amount of copper, or that amount of phosphorus, or sulfur. or plural?
How do you know?
How do I know? You doubt? You doubt that? Avogadro figured that.
Exactly. So is this guy.
He ran experiments. Okay. Well, we're gonna look at that. Yes, Emily.
I need to know. You're like, I'm not doing it. You're not doing it.
Okay. So, you are going to have to become proficient at entering that number into your calculator. Okay? So numbers like that you're going to use here. You're going to use really big numbers, and you're going to use really small numbers. So that's why I told you you need a calculator that has an exponent function. Because how long are you going to spend putting this number into your calculator? It probably won't even let you. Okay? It will? It's going to say, cut it out. Cut it out. Okay? It's not going to let you. So you have to learn how to put that number into your calculator. Chapter 4. Chapter 4, we're going to use that.
So we have to recalculate.
Oh boy. Chapter 4, it's all about math. Okay? From now on, make sure you have your calculator with you, because we're going to be doing a lot of calculations. Well, some cell phones have scientific functions on them. Yeah. So it could work, but on your test, you can't use a cell phone. You have to have a scientific calculator. Okay? All right. Okay, now let's talk a little bit about some more definitions. Chapter 1 has a lot of definitions. Okay? Well, let's review a few. Just intrinsic. What does that mean? Or not? Is that the word they use, or did they use intensive? Intensive property. Intensive property means what? It's independent of the quantity, the amount. Good. If it's extensive, it's dependent on the amount. What are some examples? Density is an example of an intensive property, right? It doesn't change. It doesn't matter how much of the substance I have, the density of that substance will be the same whether I have a lot or a little. Okay? So what is an example of an extensive property? Mass, volume, right? The more I have, the heavier it is. The less I have, the lighter it is. That's extensive. The volume, the more I have, the greater the volume. The less I have, the smaller the volume. Good. Okay, so to add to some of our vocabulary, accuracy, let's start with accuracy and precision. Okay? So, what does accuracy mean? Well, accuracy means how close did you get to the true value. So I'm running an experiment and I know what the outcome should be. How close did I get to that outcome? That's how accurate I was. Okay? So hitting the bullseye would indicate accuracy. You're right on target. Okay? You hit the bullseye. So in this example right here, 1, 2, 3, 4, 5, 6 experiments were run. Were any of those experiments accurate? One of them was fairly accurate. Okay? One of them was accurate. What about the rest of them? The rest of them were not. So in all, did this experiment go very well? No. Not very well. Okay. That's right. Now precision. A measure of the agreement of the measurement, repeated measurement. How closely do the measurements agree? If I repeat the measurements, how close are they to one another? Okay? So, is there a lot of precision in this target?
No.
It's all over the place. Mostly up in here, but there's some down here. There's not a lot of precision. Okay? So, this experiment had neither precision nor accuracy. Didn't have either one. Because I didn't hit my target, and my numbers are all over the place. So we can just pretty much scratch that experiment and start over. Okay, now look at this one. Do I have accuracy in this experiment?
Nope.
I don't have any accuracy. But what about precision?
Yeah.
Yeah. All of my data points were all around the same thing, so it was consistent. What I was doing was consistent, but I didn't get to the target. Now that could be good or bad, because maybe the data is telling me something new. I did something different, I discovered something new. Okay? Even though I was trying to hit the target. Or I need to redo it because I need to get that target. This one has what? Both. Both precision and accuracy. My experiment, I ran it, I hit my target, and my data all verifies that point that the way I ran it was good. There's precision and accuracy. Okay? So that's what we mean when we're talking about precision and accuracy in an experiment. The precision is the agreement of the data to itself. The accuracy is how close you get to the real data point. Okay? Okay. So that slide was kind of just thrown in there, but now we're going to talk about using significant figures in calculations. So if I'm going to add or subtract, then how many significant digits do I report in my final answer? Okay? There is a simple way to know. All I do is I find the decimal point of all the numbers I'm adding or subtracting. I line up the decimal point. I go to the place after, or it could be before decimal point perhaps, okay, where the significant digits, okay, the least significant digits after the decimal, and I cut everything else off. Okay? And so my answer would end up being 152.82, or I would round actually. What would this round up to? From 2 to 3, because there's a 6, right? So what if it was a 5? What would it be? Good, it would still be 3. What if it was 4? 2. I leave it as 2. Okay? So that's how I will round these numbers. Okay? 152.83. So you line it up. That's how I know for addition and subtraction. You're not going to do a whole lot of that. So, it's good to know, but mostly you'll be doing multiplication and division. And that's where we really want to focus on our understanding of the significant figures. Okay? When I am multiplying or dividing numbers, I need to count the number of significant figures in each number. How many significant figures are here? How many here? How many here? 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. So, when I report my answer, I look at the thing that had the least number of significant digits, which was this one, right? And my answer is reported in 2 significant digits. So here, the answer came out to 2.96888, etc. So I want to report it in 2 significant digits. I have to round this 9 to give my 2 significant digits. What does it round to? 3.0.
Alright.
You don't have a volume control?
No.
Okay. Okay. So 3.0. Times 10 to the negative 8. Okay? Because that's what it came out to be. Alright. That's mostly what you're going to be doing. To understand how many significant figures to report, I mostly need to know the least number of significant digits that I used in my calculation. Okay? Because otherwise, if I reported it in 4, then that would inflate the significance of this number, right? And so it would be incorrect to do that. So I have to report it in the one that has the least number of significant digits. Now, a lot of times you're going to ask, how many significant figures do I use in this calculation when the number is something like 10? Okay? If it says you have 10 beakers, let's say, 10 beakers. How many significant figures are in that number? Well, you would say 1 if you're considering how we understand significant figures, but there is an infinite number of significant figures in that number because it is an exact number. I used how many beakers? 10. I know exactly how many beakers I used. I used 10 beakers. Is there any uncertainty in that number? None at all. I know for sure I used 10 beakers. Which one? 5340. Where does that number come from? Okay. That number was not a result of counting. That was a calculated result. So there is uncertainty in it. Or it was a result of using a measuring device. And there's uncertainty in it. But if I count something, I know exactly how many there are, right? There is exactly 10 beakers, and I use that number in my calculation. There is an infinite number of significant figures, so I cannot use that to determine the number of significant figures that I record in my answer. Because I would end up recording just 1, right? But that's not the case. This does not count for significant figures because it is an exact number. Okay? So exact numbers are a consequence of counting. I know exactly how many there are. It's the inexact numbers that have uncertainty. And those are the ones that have significant digits. Okay? Okay. So they have infinite numbers of significant digits. Okay. We need to go over rounding. So if it's 5, if I'm going to round a number, it needs to be, the number that comes after it needs to be, if I'm going to round it up, it has to at least be 5, the number that's after it. If I leave it alone, then that's because the number is 4 or less. Okay? So hopefully that won't be too difficult. So 3.34, I round the 4 to 5 because there's a 9 there. So it rounds up to 5. 3.35. Okay? When would this not round to 5? If the 9 was a 4 or less, right? Then it would stay the same. It would just stay 4. Okay, let's practice rounding. Round off each number to 3 significant figures. Number 1. I want to round number 1 to 3 significant figures. What will it be? Whoops. $6.14. Because So I round that 4 to a 4 because this is a 0, right? So I don't mess with it. And that's 3 significant figures, right? It was 4, now it's 3. Okay, I want to round this to 3 significant figures. What does it become? Good. Oh, whoops. Too many 6s and 1s and dots there. My brain wasn't. Okay. What's the next 3 significant figures for the next number? Good. Yes. Okay. Because it's a 9, right? The 9 changes the 4 to a 5. Round it up. Now, something you are going to have to become very proficient at in chemistry is converting things. Okay? You have to be able to convert one thing to another thing. But for both. Yeah, absolutely, for physics and chemistry. Yes. Okay? So, if I want to convert something from one thing to another thing, what I need is a conversion factor. Okay? A conversion, my conversion factor might come from my conversion chart. Okay? So like this, let's say this was your chart. Okay? 1 foot equals 12 inches. 12 inches equals 0.33 yards, which is 1/5280 seconds of a second. Or miles, I'm sorry. Okay? So, these are my units of conversion. I want to create a conversion factor from those units. A conversion factor is a ratio. So, if I want to convert 12 inches, if I want to convert inches to yards, what is the ratio that I would use? Okay, this is how I know. Let's say I have 33 inches. I want to convert 33 inches to yards. I need to set up a ratio, okay? And this is what I need to remember. Whatever I want to get to goes on top. So I'm going from inches to what? Yards. Yards goes on top. Whatever I'm getting rid of goes on the bottom. What am I getting rid of? Inches goes on the bottom. Now I go back and I look at what the ratio is between inches and yards, and that's going to be my conversion factor. Okay? There are 12 inches in every 0.33 yards. So what number goes on the bottom? 12. There are 12 inches in every 0.33 yards. That goes on top. This is my conversion. That's how I would set it up. Now all I have to do is take 33 times what's on top, which is 0.33, divided by 12, which is on the bottom. And it's going to tell me how many yards there are in 33 inches. It should be a small number. Okay? What is it? What? Say it again. Okay? 0.098. And that would be yards. 0.908. Okay, let's write that again. You divide by everything on the, so you multiply everything across the top, and then everything on the bottom you divide by. Okay? You divide by everything that's on the bottom. So, this is how I set up a conversion. Under the 33? Under here?
Yards per second. Wouldn't you like to put a 1 under there, find this first, second, next?
If it was yards per second, so that's a rate, that's a speed, okay? Let's say we're doing, let's do that very conversion, okay? That's a good example. Let me go back. Okay, so here are my conversion factors. Let's say I was starting with 270 feet per second. Okay? Let's say that was how fast I was going. That's the speed, a rate. That's the rate of how fast I'm going, 270 feet per second. I want to convert it from 270 feet per second, let's say, to yards per minute. Yards per minute. Okay? So I come here and I say 270 feet per second, and I always put what I'm starting with out front. Okay? I want to convert it from feet to what? Yards. From feet, which could then go on where? Bottom. Because those have to cancel. Okay? If it goes on the bottom, the unit cancels. So now I've converted it from feet per second to yards per second, because I still have yards and seconds, right? Is everybody following me okay? No? So I started with feet per second, and now I'm going to put my conversion factor here for yards per feet. That's going to get rid of my feet and give me yards. And now what do I have left? I have yards and seconds because the feet cancel, right? Now, I want to convert seconds to what? Minutes. Now this is going to be backwards because seconds are on the bottom, so if I want to get rid of them, I have to put the seconds where? On top. Seconds on top, and that means what goes on the bottom? Seconds are gone. What am I left with? Yards per minute. Okay? Let's do the second per minute equation really quick. Okay? 60 seconds for every 1 minute. That's the conversion factor. Okay? That's my conversion factor. Now, yards and feet. So we go back and we see that for every 1 foot, there are 0.33 yards. For every 1 foot, there are 0.33 yards. Yeah. But yeah, you could. You could say 1 on top and 3 on bottom. Yeah. But it's the same thing. Okay. It depends on what information you have. If you have the information 3 feet for every 1 yard, then you would use that information. But this is the information they gave us. So, but it is exactly the same thing. Okay. Okay. How do I calculate this whole thing? Okay. I don't have to divide by anything because it's all 1 on the bottom, right? So there's no division that needs to take place because everything on the bottom is 1. All right. So 270 times 0.33 times 60. Divided by 1, but you don't have to do that. Okay? So what is the answer? 5,346. 46 yards every minute. Okay? That's all we have to, that's it guys, that's it for conversions. They can seem tricky, but they're really not. All you're doing is you're setting it up and you're canceling out all the stuff you're trying to get rid of, you're canceling it out. All the stuff you want to keep, okay, you don't cancel out. And that's what it is. If you learn that process, you're going to do very good. Yes. Yes. Much more than this kind. So we don't really use the American system in chemistry. We use the metric system. Okay? Which is way better. For some reason the world figured it out and America hasn't yet. But maybe one day we will. You don't have to memorize conversion factors. It would be given to you in a question, or you would be given the information. You just have to know how to use it to calculate the answer.
I don't understand math as a method, but I don't know how to go from like you don't have to worry about that. Go from like whatever it is, whatever the hell that is. You don't have to.
So that you have to memorize it. You have to memorize the conversion. Okay. Okay, well, conversion, if they're making you memorize it, you have to memorize it. But otherwise, it's something that you can either look up, or if you memorize it, then you know it. But it's not something that you have to somehow calculate, because it is what it is. There are 0.33 yards in a foot. That is what it is. And so I can use that information to convert from feet to yards. Okay? All right. Now, we are going to be using the metric system in chemistry because it is much easier to work with, and especially for conversion purposes. Okay? There are base units in the metric system. Gram, meter, liter. When that base unit gets smaller or bigger, we can use prefixes to tell us how much smaller or how much bigger. Okay? So instead of saying a gram, I could say a milligram. I'm still using that base unit of gram, but I have changed it by putting a prefix in front of it and saying milli. Milli means 10 to the third. 10 to the negative 3, I'm sorry. 10 to the negative 3. It's smaller. It's 10 to the negative 3 times smaller than a gram. That's what a milli is. Micro, 10 to the negative 6. 10 to the negative 6 times smaller than a gram. Okay? So if I was going to set up a conversion between those two things, I would say gram is 1, milli is 10 to the negative 3. 1 times 10 to the negative 3 on the bottom. And that would create my conversion factor. Okay? If I was going to go bigger, kilogram. Kilo means 10 to the third. It's a lot bigger of a unit. 10 to the third. Okay? So if I was going to create the conversion factor for that, I would say kilogram is bigger than a gram. Kilo means 10 to the third. So let's practice it right here.
You know how the little figure you got if you do the little, when you convert from grams to kilograms, you go like up 4 or whatever, and then you put the zeros in front.
Okay. Now, here it is, okay? So it gets confusing because you have to know where to put the number in the correct place, right? So, these are the prefixes. The prefix kilo means 10 to the third, right? Okay? So how do I set up my conversion? So let's say you have 360 grams, and I want to convert that to kilograms from grams. How do I set up my conversion? There is 1,000 grams in every 1 kilogram. So in other words, 1 times 10 to the third gram for 1 kilogram. Okay? That's how I would set up that conversion. So this would end up being 0.36 kilograms. Okay? 1 times 10 to the third. So a kilogram is bigger than a gram. A kilogram, 1 kilogram means that you have 1,000 grams. Okay? Is that making sense at all?
I don't know, it's just the zero, because I just feel like when we have zeros at the end, the number's bigger, so we have zeros in the front smaller. I don't get that, if you see what I'm saying.
When you add zeros to the front, it gets smaller.
Yeah. So when you
That's true.
So if I'm saying that's why it's confusing me that you saying that it's smaller instead of bigger.
What's smaller? What do you mean?
I mean, you said it's bigger instead of smaller.
A kilogram is bigger than a gram.
But what I'm saying is, when I convert it, the zero is going to convert it smaller, right? I can give you an example.
Okay, yeah.
Okay, so if it was like, how many kilograms?
Okay, I want to convert that to kilograms from the grams. So for every 1 kilogram, there's 1 times 10 or 1,000 grams.
I didn't convert like that. I use the answer that we give every time.
Okay. Okay, so 7 grams.
From there, we just add
There's 0.001 kilograms for every 1 gram. Is that what you're saying?
Yes.
That works too.
But that number is smaller than 1, is it not?
Sure is.
So why is it bigger? Why is kilograms bigger? That's not like
Because to have 1 kilogram, or to make this equal to 1 gram, I have to make it a really small number. To make a gram equal to a kilogram, I have to make it a big number.
Okay, that makes sense.
Okay?
It's like having 2 names for the same quantity.
This will give you the exact same answer. Either way you do it. So if you understand it this way, do it that way. Okay? You don't have to do it this way. It will give you the exact same answer. This way is just, for my brain, I perceive it better. I know that 1,000 grams will be 1 kilogram. That works in my brain. But if you understand that 0.001 kilograms is a gram, then do that. That's fine. Okay?
That chart that you saw in the last slide,
Mhm.
that's something we did in the brain.
No. Okay? You don't have to memorize that, but if I was to give you this information, you would need to know how to use it. And some people get confused just like we were doing here. Okay? How do I convert?
I'm okay with you doing the year stuff. If I get it,
Okay, so for example, if you have 3.567 kilograms, how many grams is that?
you gotta find out how many.
So I set up my conversion. I always start with what I'm given, 3.567 kilograms. I want to convert it to what? Grams. So they go on top, right? What goes on the bottom? Kilograms. What numbers do I put here? Okay, so let's look at this chart. Kilo is 10 to the third. Where do I put the 10 to the third? Do I put it with gram or kilogram? This number always goes with the base unit. This number goes with the base unit. Okay? So it's 1 times 10 to the third grams for every 1 kilogram. Okay? This number goes here with the base unit. That's what it means. Makes you angry? Okay, well hopefully we'll be able to manage that in here because you're going to use a lot of math. You can put 1,000. You can put 1,000. I don't care. What I care about is that you get it to the right place. Okay? Huh? Yeah, you could put 1,000 right there. You get exactly the same number. 1 times 10 to the third is 1,000. That's what it is. Okay? So yeah, it would be exactly the same. But if you get something like a mega, you don't necessarily want to write the number million up there. Okay? So you might want to put 10 to the 6th instead. But what does this end up being? 3,567 grams. Right? 3,567 grams. That's what it ends up being. What's that? Okay. Okay. All right. So we are going to be converting stuff. You are going to have to understand how to do that. I need to put out front what I am converting, and then I need to put a conversion factor behind it and multiply it by that conversion factor. Okay? Whatever I want to get goes on top. Whatever I'm trying to get rid of goes on the bottom. Okay? And if you learn that process right there, then it won't be difficult. Okay? Doing the math for that will not be difficult. All right. Okay. So what they mean here by dimensional analysis is that's what we were doing. Instead of putting numbers in first, we just put the units there and we crossed out units. We said these cancel and we're left with this, and then we put our numbers in. That's simply what we're talking about when we say dimensional analysis. Okay? And that's in physics a lot too. I'll learn that for physics. Okay? Dimensional analysis. But it's a great way, to understand if you're following the correct path to get to where you want before you even do any of the math. Right? All right, so think we're past this. How many donuts are in 1 dozen? 12 donuts in a dozen. Okay, you guys want that question first? First question on the test. Okay. Now, how many donuts are in 3.5 dozen? 3.5 dozen. And I want to get to donuts from dozen. Okay? All this is showing is it doesn't matter what it is. The process is exactly the same. Whatever you're starting with goes here in front. You multiply it by your conversion factor. What you want goes on top. What you're getting rid of goes on the bottom. And then you fill in your numbers. There are 12 donuts in every 1 dozen. Okay? And I convert it. It's that easy. Okay? Multiply everything across the top. 3.5 times 12 divided by 1, 42 donuts. Okay? Okay, so English units, we're not going to use a lot in here. Convert 12 gallons to units of quarts. Let's do that. What do I put in front? Good, 12 gallons. Now I want to convert it to quarts. That goes on top. What goes on the bottom? Gallons. Okay, so let's look at our numbers here. 1 gallon equals 4 quarts. So what number goes on the top? Good. What number goes on the bottom? 12 times 4. That's how many quarts are in a gallon. Okay? And I would divide by that 1. So, what is it? 48 quarts. Okay? 48 quarts. Convert 4.00 ounces to kilograms. Okay? So what do I start with? What is it? OZ, is that ounces? Okay? And I want to convert it to kilograms. Now, hold on a second. Can I go straight from ounces to kilograms here? I can't. But what can I go from ounces to? Okay? So, they didn't even give it to me. Okay? So let's do, what do we know ounces convert to? 16 ounces in a pound. So let's go to pound. Okay? Because from a pound, I can, here it is. Pounds to kilograms. Okay? So we're going to go to pounds from ounces. After I go to pounds, what am I going to convert to? Kilograms. From the pounds. Okay? I am doing it all in one step because I want to understand if I'm doing the right process. Ounces to pounds to kilograms. That's the process I want to follow. So ounces cancel, pounds cancel, I'm left with kilograms. So I did it right. Now let's put our numbers in. Ounces to pounds, what number goes on top? What number goes on the bottom? Kilograms and pounds, what number goes on top? 1 kilogram, 2.2 pounds. Yes. So these significant figures right here, we're not going to consider the ones that just say 1. We won't consider that because what we're looking at is how many ounces are in a pound. Okay, so we would look at this, and this would probably actually, instead of being 16, we'd probably say 16.00 if there was actually 16.00 ounces in 1 pound. Okay, so we wouldn't look at these. We would consider those more to be the exact number. Okay, so we won't consider one significant figure there. what we would consider significant figures are the 4.00, the 16.00, and the 2.2. So my answer would be in how many significant figures? 2. We're not going to concern with 4.00 is 3. Okay. So we would report it in 2 because that's the least sum. Okay. All right. So how many kilograms are in 4 ounces?
0.1.
0.0. 0.11. Or 0.12. Okay, so this is how I would do it. I would say 4 times 1, which you don't have to do, divided by 16, divided by 2.2. Okay. 0.11. Thanks.
Then you take the 2.5 and then divide that by 2.2 after you divide the 4 and 16.
Okay, I'm getting a lot of questions at the same time. So, you can multiply these two things together, find a number, and then say 4 divided by that number. Okay? You can do that. But that's extra steps. Okay? Go ahead if you want to do it that way, fine. But I'm telling you, you can take 4 divided by 16, whatever the answer to that is, hit divide again on your calculator and say divided by 2.2, and then you're not doing extra steps. Okay? You'll get the exact same answer. Exactly the same. Okay? So you're skipping finding a number and then carrying it over here and then doing another division step. Okay? You don't have to do that because 4 divided by 16, and then whatever the answer to that is, divided by 2.2 will then be the same answer that you would get anyway. Okay? So, if you don't want to have to find numbers and then rearrange them and redivide them or whatever, okay, this is how I would recommend you do that process. You don't have to do it this way. You can do it however you want as long as you get the right answer. But I would recommend multiplying everything that's on top. Multiply it across. Get an answer, right? Hit divide. Divide by the first number on the bottom. Then divide again and divide by the second number on the bottom or the third and fourth, however many there are. Okay? So you just keep dividing by whatever's on the bottom. And that way you can keep everything straight. And there's less room for making an error in your calculation. Okay? But if you want to do it that other way, it's fine. Okay? Alright, now let's look at some practice here. 5.5 inches, 2 milliliters. Okay? Let's first just set it up. Instead of going through all the calculations, which is less important, if we set it up correct, the calculation part will be easy. Okay? It's the setup that is difficult. So what do I start with? 5.5 inches. And I'm going to multiply that by my conversion factors. Okay? So let's go back and see if we have a conversion from inches to milliliters. Here's inches. Okay, inches to centimeters, but not millimeters. Okay? So let's go to the centimeters first. Okay? So, there are 2.54 centimeters in every 1 inch. Huh? Yes, there is. Thank you. Okay? Now, I want to go from, I want to go to millimeters, right? From centimeters. Okay. There's a number of ways you can do this. You could say there's they're in 10 centimeter means to the negative 2. Okay? Millimeters means to the negative 3. So it's a difference of 10. So you could say 1 to 10, or you could actually put those numbers in. Okay? For every, so centimeters,
1 centimeter is 10.
Okay, there's 10 milliliters in every 1 centimeter. Okay? Centi is to the hundredths, millions to the thousands. Okay? So it's a difference of 10. Alright, so these cancel. I'm left with millimeters. So how do I do the multiplication here? I just multiply everything across the top, right? I don't have to divide by anything because it just ends up being 1 and so on. Quantity of matter in an object. Mass is not weight. Okay? Mass is how much matter is in me. So I have a specific amount of matter in me. I weigh so much here on Earth, but if I go to the moon, I weigh a different amount, right? But did my matter change from here to the moon? No, the amount of matter that's inside of me is still exactly the same. So weight is mass times the acceleration, so due to gravity. So gravity is what's pulling on my matter that's making me weigh so much here on Earth and where I am lighter on the moon. Okay? So, but here on the Earth, we do measure the mass of something by a scale or balance, okay? Because we've standardized those so that we understand that 1 gram of something is standardized to a specific thing. So we have a standard that weighs 1 gram. If I take it to the moon, that also weighs 1 gram, so I can calibrate my my balance on the moon, and then I will have the same. I will show the same amount of matter here on Earth as I have on the moon. Okay. All right. So it's important to choose the right type of unit when you're describing something. So a dump truck, you don't want to measure it in grams or pounds. You're going to measure it in tons. Okay, a person, you're not going to want to measure it in grams, or an individual maybe kilograms. Okay, a paperclip though would be good to measure in grams, right? So we'll get into that next. Okay, length. We use the meter in science, so we use metric systems in science. Meter. Volume, we use the liter. Okay, volume is the amount of space occupied. Length is the distance between points. Volume can be described in a cube as well. The space, it's 3-dimensional. Space is 3-dimensional. So you can determine a specific volume to be either a liter, perhaps, or you could describe it in cubic centimeters. So centimeters cubed, like this is, this little cube here is 1 milliliter, which also equals 1 cubic centimeter. So if I measure the length, width, and height on that, and I multiply those 3 things, that's cubic centimeters. Now you will become familiar with cubic centimeters if you go into the healthcare, because if you're going to deliver a drug to a patient, it's usually in cc. Give this patient this many cc's, or this many cubic centimeters of this drug, okay? And that's what they're talking about. cc's is cubic centimeters, okay? Time, we measure in seconds. And from seconds, you can use all the prefixes, milli, microseconds, okay, etc., etc., okay? Temperature. Now with temperature, we don't really use Fahrenheit in chemistry, okay? Fahrenheit is not very useful to us. But what we do use is degrees Celsius. Because Fahrenheit doesn't have a very standardized method of measurement. And also the rest of the world uses Celsius, and in science we want to standardize ourselves to everybody else. We're all talking the same language. And so Celsius and also degrees Celsius was developed off of the boiling and melting, or I should say the freezing temperatures of water. So 0 degrees Celsius, water freezes. 100 degrees Celsius, water boils. Okay? So that's why this scale is pretty useful to us when we're talking about chemistry. We also use another scale. It's called the Kelvin scale. Okay? And degrees Celsius and Kelvin are on the exact same increments. So if I look at the Celsius scale, 25 degrees Celsius is 298 Kelvin. Well, if I go up 10 degrees, so from 25 to 35, I know this is 37, but let's say 35, it'll be easier measurement. So to 35, then this goes up 10 degrees. So instead of being 298, it would be 308. Okay? So it goes up and down by the same exact increments. It's just offset by 0 degrees Celsius is 273. It's offset by 273 degrees. Okay? So if I want to convert from one to the other, I just have to add 273 to the degrees Celsius. So if it is 30 degrees Celsius, what is it in Kelvin? So 30 plus 273. Whoops. So it's 303 Kelvin. I just add 273. That's all I do. It's the easiest conversion you'll ever do. But you're going to forget. Okay? So try not to. There are specific times when you will use Celsius, and there are specific times when you will use Kelvin. So we are going to try to learn when we use degrees Celsius and when we use Kelvin. Okay? Now, if you are going to convert from Fahrenheit to Celsius, this is the conversion for that. So, convert 75 degrees Celsius to Fahrenheit. Okay? So if I'm going to go to Fahrenheit, I use this equation. Degrees Fahrenheit equals 1.8 times whatever the degrees Celsius is. Here's 75 plus 32. So that's all I would need to do for that. And I have no idea why we would ever do that, because we'll never use Fahrenheit in chemistry, so this is pretty much useless to you. This one, however, you might have to use. Okay? Convert negative 10 degrees Fahrenheit to Celsius. Okay? So you're going to put right in there negative 10 degrees Fahrenheit. So negative 10 minus 32 divided by 1.8, and that's your degrees Celsius. Okay? That's how I would convert from Fahrenheit to Celsius, using that. Okay, which is not something we are going to do a lot in here. For the most part, you will always just be given the degrees Celsius. And if anything, you just need to convert from degrees Celsius to Kelvin. Okay? Alright, so we already talked about that. Kelvin equals degrees Celsius plus 273. Now, if I go to 0 Kelvin, that's the coldest temperature there is. We call it absolute zero. It doesn't get any colder. If you've reached absolute zero, that means that you have removed all of the energy from a molecule. And it has completely stopped moving. There is no energy in it. Okay? This table has lots of molecules in it, and they're all vibrating because they all have energy at this temperature in this room. But if I was to remove all the energy from all the molecules in this table, they would reach what we call absolute zero. And that's what the Kelvin scale is representing, is when we could reach that Kelvin temperature of zero. Yes?
Is it broader than degrees to
Because it's just offset from Celsius. Celsius, this is the water. This is developed for water. 0 degrees Celsius, water freezes. 100 degrees Celsius, water boils. Okay? The Kelvin temperature is developed for absolute 0. Okay? But they go up and down on the exact same increments. Okay? So it's only offset by this much. Okay? Okay, so energy, when we describe energy in chemistry, energy is the ability to do work, kinetic energy, the energy of motion, potential energy, the energy of a position. So if I am a boulder, I know that's what you guys imagine yourselves as sometimes. If you are a boulder sitting on top of a hill, this is potential energy. Okay? But as that boulder starts to roll down, it's the energy of motion. Energy is being released. That is kinetic energy. Okay? So we can store energy in a molecule. That's potential energy. It has the potential to do work. So in our bodies, we have this fascinating molecule called adenosine triphosphate, ATP, and it pretty much powers all the functions in our body. So without it, we'd be in a poor state. Have you ever heard of rigor mortis? What's rigor mortis? When every muscle in your body does what? Contracts, right? Because what have you run out of? ATP. If you don't have ATP, your muscles aren't going to function. And so when you die, you stop producing ATP, all your muscles will eventually contract because there's no more ATP. Adenosine triphosphate, it's the energy molecule. It has this phosphate, it's a triphosphate, so it's a triphosphate, so it's P, P, P. This last phosphate is shoved on there, and it has all this energy stored in it. And if I break the bond right there, if I break that bond, it releases energy, and it powers things. Okay? It allows them to be powered by that last phosphate molecule falling off. So it goes from ATP to ADP, adenosine diphosphate. Tri 3, di 2. Okay? So adenosine triphosphate to adenosine diphosphate, if you go from tri to di, that means you've powered something. You've transferred energy to something else to allow it to do work. Okay? So there's all this potential energy stored in that molecule. And that's what we're thinking of when we're talking about potential and kinetic energy with molecules. Energy is conserved. It cannot be created or destroyed. Okay? So it just gets transferred from one thing to another. So I can't create energy. As hard as I try, the amount of energy in the universe is conserved. I can only transfer it. The sun shines on our earth and our plants grow, right? So they've stored energy in that plant. Then I eat the plant, and that energy is transferred from the plant to me. Okay? So, and then I go off and I do my processes and whatever, and I release all kinds of heat, energy, and et cetera, and carbon dioxide. Okay? That goes to the plants too, and it's a big cycle, right? The energy is never created or destroyed, it's only transferred. It's only transferred. Okay? So conservation of energy. And that conservation principle is used throughout chemistry, not only for energy, but for other things as well. We're going to see it again. Energy units, calories or joules, right? 1 calorie equals 4.184 joules. And in chapter 7, we're going to use those a lot. Okay? Okay, a kilocalorie, also known as a big C calorie. Did we talk about that? This is the same calorie as the food calories. So you know how your food says there's 250 calories in a candy bar or whatever? Well, guess what that actually means? It doesn't mean 250 calories, it means 250 kilocalories, or in other words, 250,000 calories.
Wait, what?
How? Oh, it's okay, guys. It's okay. Remember how we talked about choose your units well? Because otherwise you freak out? That's why they chose their units well. Okay, so we don't freak out. How many calories does a human individual eat a day? Okay, let's say 2,000 calories. What is that? That's 2 million calories a day. We have to consume 2 million calories a day, and so they're not going to, they don't want us to put up that on their little chart saying human has to eat 2 million calories, right? So instead, they say, well, let's just say instead of a little c, let's make it a big C calorie, and that equals 1,000 little c calories. And so now, instead of 250,000 calories in your candy bar, it's 250. Okay, that bodes with us a little better, right? We don't freak out as much if we're eating 250 calories as if we're eating 250,000 calories, right? But that's the way it is, okay? All right. So yes, the food industry has tricked you all your life. Okay. All right. Concentration. We're going to use concentration a lot in chemistry. Obviously, solutions are at specific concentrations, and those concentrations will be important to chemical reactions. Now, this is the last thing we're going to talk about for chapter 1 is density. So density is the ratio of mass to volume. It's an extensive property. Okay? Used to characterize, I'm sorry. Density is not an extensive property, but mass and volume are extensive properties. Okay? Density would be an intensive property because it doesn't matter how much of it you have, the density would not change. We use it to characterize a substance as each substance has unique density. So if you determine the density of something, you could actually find out what that thing is if you did a really good job of determining the density. Because everything, it's like a fingerprint almost. Everything has a unique density. So if I know exactly what the density of that thing is, I can use it to characterize. And we did that in the lab, if you remember. We found the density of some things, and then we found the boiling point, and then we found its solubility, and we identified what it was. Okay? Because those are its fingerprints. So, units of density, this is the one that you need to be most familiar with. Grams per milliliter. Remember I told you milliliters are the same as centimeters cubed, and centimeters cubed is the same as cc. Okay? So these are the units of density that you would see. All right? But this is the one that you need to be most familiar with. Grams per milliliter. All right? So densities, so this is a liquid. It's a liquid metal. It's mercury. Its density is actually greater than this nut. So the nut floats on top of the liquid mercury because the mercury has a greater density than the nut. And then water has less of a density than the nut. And so it's on top of the mercury, right? And the cork has the lowest density. So it's floating. So you can separate things by density, okay? And they will float on top of each other. So oil and water, they won't mix, but one will be on top of the other one because one is less dense than the other one. The less dense thing goes on top. So the oil goes on top because it's less dense than the water. Water is more dense. So here's some common densities. Air obviously would have a very, very, very small density. If you look at the density of air here, it's 0.00129. Right? That's because all the molecules in the air are very far separated. So obviously the density would be very low. If it had a high density, higher than a human density, then we would float on top of air, right? But that's not the case. Air floats on top of us because it has a lower density. Ammonia, benzene, bone, carbon dioxide is gas, so it has a low. Any gases at room temperature would have low densities. And so temperature densities depend on temperature. Did they tell us the temperatures here? Okay, so they're showing us over here. Okay. So this is at 0 degrees Celsius. So I guess a lot of these are at 0 degrees Celsius. So that's freezing temperature of water. So this is a gas at freezing temperature of water. Ethyl alcohol, 0.789. Gasoline, gold. So gold has a high density. So it's a heavy material. If you have a little bit of it, it's actually pretty heavy, just a little bit of it. Okay? So because it has such a high density. Lead, mercury, gold actually has a higher density than lead and mercury as well. Okay, so it would be heavier than those two things. If you had the same amount, volume of them, then gold would be heavier. So, how do we calculate density? Well, this is the equation. It's very simple. Density equals mass per volume. I could ask you 3 questions about density. What is the density? What is the mass? What is the volume? Okay? So, how do you answer? So density equals what? Mass over volume. What does mass equal? Take V here, and where do I move it? I move it up top, so it's on the bottom, so I have to move it up top to the other side to get mass all by itself, right? So mass equals density times volume. What does volume equal? Well, if it's like this, mass equals density times volume to get volume all by itself. Volume equals mass divided by density. Okay? So it's simple algebraic rearrangement. Those are the 3 types of questions. So if I asked you what is the mass, what do you have to be given? Density and volume. So you look for those 2 things in your question. Okay? Well, if he's asking for mass, then what is my density and what is my volume? If I'm asking for volume, I must have given you mass and density. So you look for those 2 things in your question. So 200 centimeters cubed of aluminum are found to weigh 5.4 grams. Calculate the density in units of grams per centimeter cubed. Grams per centimeter cubed. That's easy. Density equals the mass over the volume. 2.7 grams per centimeter cubed. Okay? So that's all I really am trying to do for that. Air has a density of 0.0013 grams per milliliter. What is the mass? So if I'm asking for the mass, what else do I have to be given? Density and volume. Where's the density? 0.0013, good. What else am I given? Volume. I am given the volume. Now in this case, they gave me the volume in liters, which for a gas is okay, because gases are so tremendously spread out that putting it in a liter volume is not necessarily that bad. Okay? So how would I calculate the mass of the air in a 6-liter volume? Mass equals density times volume which is 0.0013 grams per milliliter, times, oh, I can't use liters here because my density is in what? Milliliters, so I have to convert it. Okay? Well, liters easily converts to milliliters because it's only 1,000 times difference. So instead of being 6 liters, it's 6,000 milliliters. Okay? And then the milliliter units will cancel, and I'm left with grams. Okay? So it would be 0.0013 times 6,000. Okay, calculate the mass again. Mass. So I need to be given what? Density and volume. Did you find them? They're in the question, right? It's easy. Calculate the volume in milliliters. What am I looking for? Volume. So what do I have to be given to find the volume? Mass. Did they give me the mass? Did they give me the density? Okay. See? Density questions are not difficult. I can ask you 3 of them. If you know how to solve for the equation, then it will be easy to find the information, extract it from the question to put it in your calculation. Okay?